goal will be to look at this thing here, which is a RISC-V based IoT platform, originally from Microsoft, but now I think it is it got turned into like a standalone platform or something. And it's basically using the CHERI extension of RISC-V to build kind of very safe IoT devices. And CHERI is basically sort of a long-standing research project that tries to build in security into the foundations of a microprocessor. And I don't know too much about it apart from chatting with people over coffee sometime. And I haven't really looked into it too much, but the goal for now would be to try to see whether we can make this thing work with Pydrofoil. And Pydrofoil is my PyPy based emulator generator that takes SAIL definitions of instruction set architectures and turns them into decently fast emulators for the instruction set architectures that are described by the SAIL models. And CHERIoT happens to build on top of the SAIL model of CHERI RISC-V. So I thought that it would be a fun experiment to try to see whether we can use that. But we can use Pydrofoil to make the emulation of the CHERI RISC-V processor that CHERIoT is using faster. And the good news is that like one of the most annoying bits of doing any of these things is always that building everything is always super complicated. I mean, for CHERI RISC-V, you need an LLVM, fork of LLVM, cross-compiler, and you need to sort of set up things in just the right way, and sort of that's always incredibly frustrating. But the good part is that the CHERIoT project has a very nice dev container setup, and it has nice CI workflows, and the CI workflows use the SAIL-based emulator, and so this takes away a lot of the super frustrating bits of trying to use of basically embedded operating system development. And I want to make it clear, I don't plan to work on the real-time operating system at all. I just want to sort of use it as an example of something to run on the CHERI RISC-V device. So let's see. This is the checkout of the operating system for CHERIoT, and there are a bunch of examples in here. And I built the Hello World example already. And it's here, and it's a RISC-V 32-bit executable using the CHERI RISC-V dialect, and we can run it with the SAIL-based emulator. So we can say, where's the SAIL-based emulator? Here, C emulator CHERIoT sim, and we can use that emulator to run the Hello World example, and that will do a bunch of stuff. And one of the things it does, it prints Hello World, and then it terminates. And oops, oh, thanks for the warning. Hi Nico, good to see you. My mic is low. How is that? Is that any better? I can also try to turn the terminal bell off, because that's probably a little bit annoying. Maybe no bell. Is my voice coming through a little bit better now? I think turning the bell off probably already helped somewhat. Nico, please tell me if... okay, excellent, thank you. Right. Okay, so the goal will be to take this program, this binary, and replace the slow Sail-based emulator with a PyPy-based, Pydrofoil-based one. And that's what I want to investigate. I have no clue whether that's realistic or easy, but basically I want to like use the next hour or two to kind of look into that a little bit. Okay, let's see. So the Sail-based emulator is here, and that's basically I think it's like an extension of the RISC-V emulator, yeah, like the regular RISC-V emulator. And on top of the regular RISC-V emulator, it adds the CHERIoT extension, which adds a bunch of security features to the instruction set architecture. We can look at those a little bit. Right here. I don't really know how any of this works. Ah, no, that's in, let's see. Source. There's a source directory. Right. Source. Cherry inst sail. Cherry types. Right. Right. So basically, the Cherry extension for RISC-V seems to be a bunch of extra files that get added into the regular RISC-V sail model. And so the first step that what we will have to do is we will have to take all the sail files of the Cherry RISC-V emulator and compile them into a text-based ASCII format that's already type-checked and removed a few of the like difficult parts of Sail, so that Pydrofoil can start working from that. And I haven't worked on Pydrofoil in quite a while, so I need to sort of remember how any of this works. Here's my checkout. Okay. Let's make a new branch. CHERIoT. Okay. And I will have to garbage. Oh, no, that's fine. So workflows. No, GitHub workflows. Pydrofoil. Okay. I can use it. Look at my own CI scripts to remember how things work. So translate. Okay, there's a makefile apparently. Regen sail IR files. This is what we'll have to do. And apparently there's an sail binary here. What's it called? Right. This is what we have to do. Let's try this. Not here. Here maybe. No. Okay. I hope it's not too weird to watch me fail at doing complicated build stuff. But so, yeah. No, that didn't work. Okay. Let's see. Can I just how do it work again? Region files. Okay, obviously something weird like that would happen. Where's the makefile? No, ILA sail. Export path. Ah, I need to add something to the path too. Okay, fair enough. I can do that. Let's try it. Right. Oops. This is makefile versus bash problems, echo path. And I have this, right, Isla sale. Okay, that works, excellent. Cool. So now I need to find out what, I mean, the build tooling of sale is pretty weird. And I'm probably also holding it wrong somehow, but the goal will be to find out which of the, which of the source files, the sale files we need to include. And I think the easiest thing to do for that is to just regenerate the emulator and then look at the command line. So if we say make, what's the CHERIoT? Oops, not the wrong one. CHERIoT make C emulator. We want to make the CSIM, right? Make CSIM. Right. And basically we want to do this stuff, except that we don't want to use the standard sale, which would build a C-based emulator, but we want to use the Isla sale. Let's try that. Cannot use multiple. Right, so I need to remove this here and replace it with nothing, maybe. Cool, something's happening. That's very good. Oh, wow. Okay, something happened. So where does it put it? It puts the output somewhere into, what's the -O here? Here. Right, it's there. Amazing. Okay, this was by far the hardest part. Let's see. Right, cool. This is the actual input that we need to look at now. So what we did now, we took the description of the Cherry RISC-V instruction set architecture, and we transformed it into a much simpler syntax, which we can now like do more stuff with, because it's been type checked and it's been transformed into sort of a very regular syntax. And basically Pydrofoil takes this file and then it parses it and does uses it to generate like an emulator including a just-in-time compiler for the Cherry RISC-V architecture, starting from that file. Right. So let me put that command line into my notes, because that stuff is always the hardest part to get back. Okay, good. And now we can move this file somewhere, copy this file somewhere. We need a CHERIoT something directory, which we don't have yet. So what's the make dear CHERIoT, and what's the input? Is it input? No, it's generated maybe. I don't know. Okay, it just goes in there. So we just put it there, and now we have the IR. Excellent. And now we need to do a bunch of sort of a little bit boring. We need to do a bunch of a little bit boring copy paste work from the RISC-V code. I kind of even wonder whether just to make this less annoying to just yeah, no, that would be too weird. Let me do the proper thing here, which is to like copy a bunch of the infrastructure from RISC-V. I want to rename this file name to CHERIoT model RV32 IR, and now we can copy a bunch of the RISC-V stuff, like the support code maybe, and the empty init file, and the target, which is like a makefile for RPython. And then we need a new test directory, test, and an init file in there. And now we need to, let's copy one of the RISC-V tests to CHERIoT test CHERIoT.py. Okay, and we also should rename the support code RISC-V, support code CHERIoT, and target RISC-V to target CHERIoT.py. So, okay, now we can, wait, I already have another editor. Let's see. Now we need to start like editing this code, and I don't completely know how to do that. Let's look at the target first. Oh yeah. Yeah, this is a little bit stupid. There is no, I mean, originally I only had an emulator precisely for RISC-V 64 bits, and now I'm growing sort of emulators for different languages, but I don't really have proper infrastructure for like sharing like build tooling for the different infrastructures that I support right now. And I mean, there are partly good reasons for that, because like ARM and RISC-V and CHERIoT, there's kind of different enough that it doesn't necessarily even make sense to try to share stuff between them. But yeah, eventually I need to do something, because all this copy pasting is getting a little bit annoying. Oops. Okay. So CHERIoT import. Okay. And I have some entry points that are probably the same between CHERIoT and RISC-V. And let's kill this. We don't need the hack. We can kill this too. We have 32. Oops. We have 32 bits only. What is it even used for? I don't know. Let's kill this. Nothing, it seems. Out. CHERIoT Py. And now we can import things from CHERIoT. Okay, excellent. CHERIoT. Oops. What's the get main thing? I don't remember that at all. It's probably a little bit weird. So there is no 64-bit variant of CHERIoT. So we can kill this. means we can kill this too. This is a little bit boring, sorry. And the target is just make code, which gives us a main, and then we can translate things. Okay, cool. So makefile is done. We'll probably need like 17 fixes. CHERIoT, support code CHERIoT, and write. I want to kill this. We don't have support for that. Let's just not have a version flag for now. And a whole bunch of the other command line options don't really make sense either. So let's see. I will just ruthlessly kill stuff. We don't have a help text yet. Use the CHERIoT. Okay, let's see. Yeah, there's a device tree. I don't think we need a device tree. Yeah, that will be one of the difficult questions to find out later. But the rest could probably just stay, maybe. I call get main somewhere. Main, that's fine. But it doesn't need an RV64 because there is no such thing. RV64. And so okay. This goes away, this goes, oops. Right. I don't really know what the ISA spec that the device tree reports looks like. I don't think we need a device tree for now. I don't know. We'll find out. Actually, we should check what the C emulator does for the device tree. So what happens when I run this? I really wonder what happened here. Why does it print me illegal Unicode characters as part of the help? Does it allow? Oh, it allows you to pass the device tree blob. Okay, so maybe we do need one. What is that? I mean, this is so weird. Where does it even come from? Say disk 5. Trace output. What is that? I don't get this at all. This is very strange. I don't get it. Okay, it's not a big problem anyway. So what does it do about the device tree blob though? Maybe nothing. And if there's no DDB, it doesn't do anything. Okay, fine. So we don't need, we're not going to fake any kind of device tree. Oops, no, I'm not here. Okay. The next step would be to try to adapt the test. Okay. So that's going to be a whole bunch of search and replace. here the only elf we have right now is the Hello World elf, which we're going to have to put there. We don't have Linux yet. We don't have dry stone, anything like that. So, and then there's parse full CHERIoT, right? CHERIoT IR. Yeah, that's wrong though. It's 32. Let's start with the parsing anyway. That should actually work. That should be the only thing we need. So the only test we need. If we import the elf now, we might be able to just like actually start a test and see it fail spectacularly. So let's see. Did I copy it already somewhere? I don't think I did. Here. Hello world. We'll copy that. There's also a dump file. Let's actually look at the dump file. Is that like an obj dump or something? Wow. How large is all of this? It's a 1.5 megabyte binary. Okay, excellent. Wow, why are they... it's lots of debug stuff, right, fine. I would really like to see some of the disassembled instructions somewhere. Freestanding code. I don't even know. Scheduler code, right. Okay, let's go to the bottom. Right. Okay. So it does contain the disassemble code. It contains a bunch of unknown instructions. That's great. I wonder whether the unknown instructions are because they've been using obj dump. They've been using a RISC-V obj dump, which doesn't know about the Cherry extension. I have no idea. Right. Yeah, those unknown instructions are a little bit annoying, but fine. Okay, that's I'm getting sidetracked again. The thing that I want to do is I want to copy this thing into my testing. What is it? Test input. I don't have an input directory yet. CHERIoT input. Okay. Oops. No, it's not in test. It's just directly. Okay, good. So now we maybe have a chance to run the test. I don't quite know. Let's try this. PyPy 2 bin pytest on CHERIoT. And yeah, I should. Right. Okay. That's to be expected. What did I get wrong there? CHERIoT. Oh, it's simply lowercase. Okay, I can close this again. Right, it's here. First thing that I got wrong. RV, same here. Okay, oops. What? Okay, it's parsing the IR. That's great. And then I mean, that's the most important part, right? It manages to actually take in the input and then do something with it. And then what I don't completely understand is why does it skip this? I don't completely get that. Let's see. Oh, because I didn't put the elf in there. Okay. What does it say if I ask it for the skip reason? Got empty parameter sets elf. Okay, fair enough. That makes sense. So it's, what did it look like before actually? Okay. So I will just put hello world in there. And what happens then? Right. Okay. I missed some. 5. It should be CHERIoT IR. Right. Okay. Let's see. Cool. So it's now turning. Ooh, wow. Okay, that's scary. We got. Okay. So what I do sometimes when I don't completely know, this is basically an internal compiler error from Pydrofoil, in a kind of a scary place, right? And oh no, I did not need this now. So what's happening here is that so we're taking the description of the CHERIoT instruction set and we want to transform it into Python code basically as a first step. And that Python code happens to be our Python code, and then later we can take the R Python code and compile it to C. And while compiling it to C, we can also like automatically put in a just-in-time compiler that will take CHERIoT instructions and translate them at runtime to host machine instructions, like x86 instructions in this case. And this compiler is actually fairly complicated, and it's it's basically a full static compiler for the weird intermediate representation of Sail. It's not that weird, but the intermediate representation of Sail. And to be able to do that, there's a bunch of algorithms in that static Sail compilers, Sail to RPython compiler, that are a little bit complicated. And one of them goes wrong here, which is very frustrating. So let's see. Did it actually generate anything? Is there some output we can inspect? CHERIoT generated. Oops, I didn't make. Did it print things? No, it didn't. Okay, so let's run that again, and the compiler will the compiler gives me a debugger inside the compiler to be able to sort of inspect the functions that it failed to like do something useful for. And now I need to sort of remember. Right, I kind of expected that. Maybe we can work around this problem for a little bit if I remember. Let's try. Does this work? Ooh, wow, that looks scary. Maybe we can circumvent the problem for a while. That would be really useful. Pydrofoil, split graph, split completely. Do I need to split this? Can I just always raise can split error for now? I mean, basically, this is obviously a bug in the Pydrofoil static compiler, which I have to fix, but it's kind of not really what I want to work on now. So if I can just ignore the problem for like the next hour, that would be nice. Right. Cool. It's doing something. Right, and now we have a boring problem. I forgot to make the error file. Let's try again. Ah, yes, and it's kind of an equivalent problem. I need to give it an empty init, otherwise it's not a Python package. And it's py boring. What's happening here? Ooh, now it crashes. Okay, that's weird. What's going on here? So now we're getting a crash in the automatically generated Python code, and now we need to find out why that is basically. But basically, we have generated Python code, and something's weird in there, and we need to find out why. Okay. But what I want to do now is I want to add all this stuff that I did to the repo, CHERIoT support code, CHERIoT target, CHERIoT test, init, test, CHERIoT. We have all the inits. No, I'm missing the one I generated. Wait, no. Git set. I don't wanna add this. Cool. Okay. So now what we wanted to do was find out why this crashes. So there's a function cap to encap, which is capability to encoded capability, I would guess, right? And that failed somehow. And we need to find out why. And for that, we will go into the source code and grab for that function. What was it called again? Cap to encap. Cap to encap. Right. So let's look at the CHERI source code. So source CHERI cap. Was it? No, it's CHERI regs. Regs, that's the registers. Cap to enc cap. Right. There's a let here. Write the register with a capability value. Okay, great. So we have a register, and we want to write a capability value, and to do that, we're calling cap to encoded capability, and then we're doing end capability loop something. So let's look at the definition of that. It's in CHERI cap common. Right, it's here. This represents a partially decompressed capability. The permissions E and O type are expanded from their compressed format by enc capability to capability and compressed by cap to enc cap. And here we have it, and it takes a capability and it returns an encoded capability. An encoded capability is a struct, and that's the capabilities as they are stored in memory. And that's basically some kind of bit field, right? There's one bit, and then capability C perms width, so it's a bunch of widths. And bits, the bits type in Sail is a bit vector of a fixed width. Right, and so here we encode things, and then what do we do with V? We assign it to one of the registers. Okay, that makes some sense. So where does it fail? It fails in... Let's actually run it again so we can inspect it in the debugger. We can also open the CHERIoT generated. We can open the generated code, and it fails in which line? Yeah, the generated code is actually very scary. Here, right. Interesting. Why does it not exist? It does exist. Right, so we probably have some kind of weird ordering issue, something like that. Like we're trying to run this function here before... No. Okay, I don't quite get it yet. So we are in the function, and setcap to encap doesn't exist. And where am I here? Didn't I just find it? I'm confused. What? I can see the function right here. Why does it not exist? Is that the right term? Oh. What? I'm very confused right now. Oops, I shouldn't have done that. Yeah, the debugger is actually a little bit overwhelmed by the amount of code that I throw at it. I mean, it's like 78,000 lines of generated code that I'm trying to sort of debug here. Ah, I see, right. So we're calling let_init in the middle of this big module, this big automatically generated module, but then the function that we're calling from the let_init is actually only defined sort of further down. So we would have to move the let_init further down in the file. Let's actually just do that, just to test the theory that that's the problem. And so. I would just hack stuff for now to verify the theory that this is causing our problems. Cool. Yeah, it works. It gets further. It crashes somewhere else. So that's the right fix. So now I need to understand why is let_init make code let_init. Let_init is called before defining all the helper functions. It's possible that this is only a problem for CHERIoT and not for any of the other Sail models that I'm supporting so far, because because the others aren't doing anything complicated in let. So I'm just going to switch this around. This defines all the other functions that should be defined, and then I'm calling let_init at the end. That looks very reasonable to me. Let's try to see that. We can also fix the other problem, RV64. We were about to fix that maybe. Anyway, let's return true. Right. Let's see. Okay, it crashes somewhere else. It's always good. So there's a syspmp count that we don't have, it seems. So what is syspmp count? So basically, the way that these emulators work that you can generate from Sail models is that a bunch of things are defined as part of the Sail source code, But then there's also a bunch of sort of handwritten C code that the sail model will interact with. And that turns into support code in the Pydrofoil, which is just Python functions. And I kind of have to sort of manually port the C code to Python. And it seems that sys PMP count is something that I don't have yet. So let's find out. Sys PMP count. PMP is the physical memory protection. Right, and it's defined in C. And I need to find out where. Right, it's here. Let's look at it. Sys PMP count. And it returns an integer. Right, that makes sense. And it's something that you can control from, I don't know, the command line maybe? I don't know. Here, yes. Platform impl. Right, by default it's 0, and then it's the other file called riskvsim, and that is something you can set from the command line, and but you must pass values 0, 16, or 64. And it's one of the weird ones. It's one of the weird, not really valid command line options that we've seen, that which I don't understand yet. So let's try to see. Oh, wait. Yes, PMP count, and you pass it this. But I think what this shows me is that by default we can run the Hello World example without passing this option. So that means for now we can PMP enable PMP is false. For now we should be able to get away with just returning 0 and saying that we don't have any physical memory protection regions. So this is zero. Fix that later. So let's see. Let's try again. Oops. Nonsense. Wow, it's doing something, right? It loaded the ELF file and it found the entry point, and then it did something, and then it started reading from emulated RAM maybe. Right, but we don't have a helper function that tells that returns the UART base, which is like the at which address the UART is memory mapped. And I'm a little bit confused because UART. Okay. Maybe I'm missing something from the RISC-V model. I missed an update or something like that. Let's see. Here. It's in the platform code. UART base. What is that? And it's just a fixed address. Yes. Right. Cool. I think that's new. That used to not work like that. Maybe. So we basically need a function that returns the UART base. So it looks like this. And machine return. Let's just return the constant for now. We should actually do it properly and make it like configurable, or make it some kind of Okay, let's try again. Okay, UART size, excellent. What is it? It's 100, okay, let's do that. Oops. Moo, it's running instructions. Amazing. I never thought we would get there in like an hour. Okay, that's the debug output, but wait. I thought I saw it running some instructions. Ah yes, I scrolled too far, I think. Okay. Set. Let's get rid of the old output. Right, it is running instructions. Very cool. Bloop, bloop, bloop. And now it has C set bound as exact, bounds exact. So that's probably capability set bounds exact. That's one of the cherry extension instructions that sets the capabilities of something. That sounds plausible, and it's missing something, which is sail truncate LSB. Okay, now it's getting annoying. Let's see. That's truncate least significant something, I suspect. Right, and it's not there. And it's probably also not there. Okay, I need a new terminal tab, I fear. Sail. Oops. So basically, Sail has a big runtime library for operations on bit vectors of arbitrary size and of like arbitrarily sized integers. And I suspect that this is one of them. Yes. And it's, I mean, I ported most of them, but not all of them. So, sail truncate LSB. Wonderful. So let's see. So it says it's similar to vector subrange L bits above, right shift the LSBs away. Okay. So it's truncating the bit vector to a length that should be left. So it takes the length of the bit vector and then it shifts out the lowest total length minus the result length, and the resulting bit vector is of rlen, which is the length of the result. Okay, we can look at where we crash. What are the arguments? We have this is the call, and we have the first argument is this, right? The second argument is 23, and the resulting argument should have length 32 minus 23, right? And that's basically, that means we should remove the least significant, the 9 least significant bits, right? Okay. That's a little bit more work. We need to go into the details of the bit vector implementation. Pydrofoils, bit vector. And it's also sort of, I mean, this stuff is always very fiddly, and it's also very high cost to get it wrong. Because if you get it wrong, we will just have to sort of get the wrong bits somewhere deep in the details of the capability implementation, and we will just sort of be extremely unhappy and hunt the bug for like a very long time. So it makes sense to sort of carefully think about what's happening here. But yeah, I mean, from the comment here, it's similar to vector subrange, and we do have vector subrange, right? Yes. So we should implement truncate LSB by implementing it in terms of vector subrange. Do we have truncate without LSB? Truncate. Yeah, we do. So we do have truncate, and it says how is truncate implemented? Truncate. Right, it does things. But it's not implemented in terms of vector subrange. Yes. And yeah, I mean, this is trivially easy to get wrong. To get an off by 1 error, so we should be very careful. Do we have count leading zeros? Count. Okay. So that means that's the next thing we'll have to do. We have to implement truncate LSB and then also implement count leading zeros. Right. So we should be, yeah, we should do that. We should be extra careful here. So yeah, I mean, let me do the following. I want to look at the diff. I want to check all of that in. Do not all of it. Yes, that's a real fix. Yes. Yes. No. Yes. Yes. Facts to progress. And now we need to switch gears a little bit and start implementing some sale functions that we're missing so far. And the first sale function that we're missing is say truncate LSB, and then the other one we're missing is count leading zeros. Okay, and yeah, we still have a PDB here, which means we can use this as example values. Let's write a test first. Truncate. There's a truncate here. We can copy that. Truncate LSB and yes. So this is a bit vector of size 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we truncate, we basically get the 2 highest bits, and that's these 2. And if we truncate LSB 6, we should get 1, 2, 3, 4, 5, 6 these bits. This. Except that we want it in binary, and that's where we want to get to. And then, so we need to implement truncate. And truncate, like truncate LSB, truncate is sort of done a bit too clever in my opinion. Let's just have a generic implementation here. Truncate self I, and So we want a subrange thing. And we just need to be super careful because it's super easy to get off by one errors. Subrange gives the highest index and the lowest index of the range that we want to extract from the bit vector, and both bounds are included. So it's not like Python where the upper bound is missing. But we should be able to implement truncate LSB in terms of subrange. Self.return self.truncate subrange, and first we want the higher number and then we want the lower number, and since we want to leave off the least significant bits, we want to so cut off is is it length? What's the size? Self.size minus I. That's the amount. That's where we want the index where we want to start. Maybe -1. I don't know yet. And where we want to end is self.size. But this is wrong because I'm sure there's an off by one error somewhere. But we can actually debug that in the test and try to sort of see what's going on. Pydrofoil test support code truncate. We get a debugger, and what's self? Self is this bit vector here. We can look at the bin of that. This looks like the test, right? Yep. Ah no, wait. Yes, good. And self size is 10. And I is 2, and cut off is 8. And then if we step in here, we have N and M, and the width is now, okay, so the order is wrong. That's the first problem. We should, number 1, but then also the difference, even if we change the order, we get the wrong size, I think. Let's try again. Next width is 3. So either the first argument needs to be one smaller, or the second one needs to be one larger. Let's see. So I think we should actually subtract 1 here. And we can probably convince ourselves that if we pass the size here, I'm not sure. Let's just try it. Self.subrange self.size, and cut off is -1. That's wrong. It should be +1. Yes, that makes sense because the bounds are inclusive and we don't want the cutoff bit. Right. Okay. That looks sensible. Except that we're not getting the right result. Okay, that's frustrating. Okay, there's still an off by one error somewhere. Or maybe also the test is wrong. That's also entirely plausible, right? Let's count the bits again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, we would expect the result to be 2, not 1. Okay, that's strange. Okay, let's look at the debugger again. suspect that, yes, I suspect that I got the upper bound wrong because size isn't a valid index at all. So I need to, yes, this looks more plausible. Right, cool. And yes, we should actually be good and write also a test. Here's a hypothesis-based test for truncate, and I think we want to do that too for truncate LSB. So let's copy that. So what we do in test truncate LSB is we generate a random bit vector and then get the bit width of it. Then we either we draw something between 1 and 64 to test sort of the small bit vector corner cases, or just in the full bit width, and then we get the target width. And so what's the value? I'm confused. What is it doing here? Wait, what? Okay, this test is just broken. We don't need that at all. Okay, the truncate test is also just wrong. We need to like consider whether we want to like fix both of the tests or just focus on truncate LSB. But this is wrong. We're giving a bit vector. We want to truncate it. We compute a random truncate width, and so what we should do is we should say res bit vector dot truncate to LSB to the truncate width, and then what should be true is if we shift the input vector by the size minus the truncate width, then the lowest truncate width bits should be the same between the result and the shifted thing. Let's try that. So first let's check that the size is actually the truncate width, right? That must definitely be true. And then the other thing we want to check is that is there a shift? Do bit vectors have a shift method? Shift, L shift. We want an R shift. Yes, they do have an R shift. Okay, so we want to bv.rshift bit width minus truncate width, and now if we take the lowest bits, it should be the same as too long. And that should be the same as the rest of too long. It's called too long because it produces a Python 2 type long. It's not really the C type. In Python 2, which our Python is unfortunately based on, in Python 2, there were two integer types, one called int, one called long, and int, and I mean, they were automatically converted between each other. And int was basically for machine-sized integers, and long was for arbitrarily large integers. And so the toLong API exists basically for tests. And we can also like do a bunch of prints, bit vector, truncate width, res, other res. Oh yeah, let's do that. Right. Right, here we have the hypothesis tests, and we do something like we truncate the sparse bit vector of width 123 with the value 66 to target size 6, and since the 66 is very low, we extract lots of zeros. That makes sense. Right, cool. That looks plausible. Let's look at another example. This one. we have a generic bit vector of size 556 with this value, and we extract 42 bits, and the result is a small bit vector of size 42, and with this value, and the shifted bit vector has this value. Okay, yeah, looks good basically. Right. So now we have implemented the bit vector method. Now we need to hook it up with the support code. So we say def sail truncate LSB, checks the machine, bit vector and a size, and we return the bit vector dot truncate LSBI. And we can say that the second argument of this is always an int. Right. Okay, and now we can sort of go back from that to CHERIoT. Now we've added one more function from the support code, which is basically this C library of stuff that Sail instruction set architecture models can rely on. And as we already suspected, we're now failing in the next line here, which is count leading zeros. Okay, that's more annoying. We need to find out what that does. But let's do a commit first. No, that's still a hack. Yes, 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 yes. No. Okay, what else? Ah, yes, before I do the count leading zeros, I want to fix the second hypothesis test because it's just weird. Yes. BB.too-long. Oops. BB.too-long. Yes, fine. This string manipulation expression here looks very scary. I hope somebody convinced themselves that it's correct. I suspect it was me, but right. Okay. Okay, good. So now it's count leading zeros time. Let's look at the example again. We have a what are the argument types? We're passing a small bit vector. Does Python have it? No, it doesn't. Right. So let's look at the Sail implementation of this. Cool. It's in sail.c again, I suspect. Okay, let's find it here. Yeah, it's here. Right. And it's using, I mean, Sail, the C version of Sail is using the GNU multiple precision library to implement the bit vectors, which is one of the reasons why the C-based emulators for Sail are very slow. And so what it's doing here is it's calling the GMP function size in base. Okay. Size in base 2. Right. And then it's doing length minus the size in base 2. So it's computing the bit length. That makes sense. And then afterwards it's saying the zeros must be the length minus the size in the base, right? And I think we might have, we have something like a bit length operation. I don't remember. Width. No. Okay, there is a bit length implementation in Python though. And we can look at that. I think. Bit length. Yes. Wow, this looks very scary. I don't get that. Right, this is basically a very stupid manual implementation. We can do the same thing. But yeah, we should be extra careful again to make sure that we're not screwing this up. Okay, let's actually Google, oops, let's Google count leading zeros. Right. Okay, let's get started. So again, we start with the test. An example test. So we do this thing again. And we know that this is the 10th bit, so there are no leading zeros. Oh, hi Matti. It would be very sad if I had just not been audible the whole time. I suppose it's possible. Nico was there earlier and could hear me, so maybe it is you. And I see stuff here on the mic. Can you check again, Matti? Good to see you in any case. Are you still not hearing anything, Matti? I can see you in the chat. I cannot reply in the chat because I didn't log in on my phone. I really didn't stream in like a year. I can also, if he cannot hear me, then he cannot know what I'm asking. Or something. Okay, I will continue for a little bit. And Matti, please. Right. Count leading zeros. So this is the first case. The highest bit is set, so it should be, the leading zeros should be 0. So now let's do 1, 2, 3, 4, 5 leading zeros, and that's that. Right. How do we do that? I want to do that do it in a very bad way for now. We can always optimize it if it turns out to be a problem. So def count leading zeros. I think there's a function that extracts 1 bit. Is it called read bits or something? Yeah, it's called read bit. And so what I want to do is for I in range self.size -1 to -1 exclusive with a step of -1, and count is equal to 0, and if self.read bit I return count, and otherwise we increase count and return count at the end. So we can do break here. Right. That looks plausible. And the test looks fine too. And so we can, oops. Count. And that works. And I even kind of believe it because the test wasn't very complicated, but let's make sure that we write a hypothesis-based test too. You can also remove the print again that I added. We don't need extra random data for that. So we just have a bit vector, and we can get the res is b.count leading zeros, and we should make sure that assert res, let's start in the boring way, right? The number of leading zeros can be anything between 0 and the size. So this should pass immediately, right? But then, of course, we also want to have a more precise test than that, and for that we can convert the bit vector to a long, and then we can we convert it to a bin, a binary number. Then we need to take off the 0b, which is this slice here, and then we need to adjust it to the bit width by adding 0 characters, right? And let's print that and bit vector to see what that looks. Fine. Oops. Right, okay, it gets extended, and so now we want to count the leading zeros, and so then leading zeros is if we take this thing here, and if we zeros, if we L strip the zeros, then assert res equal to len of aster minus len of aster zeros. Right, the number of zeros that we removed, oops, equal aster, that we removed should be the result of our count leading zeros operation. Let's try this, and it passes. Excellent. Cool, maybe. So now we need to hook it up again. So here we are. Right, count leading zeros needs to be in support code, and it takes a bit vector and it returns an integer, and that's a boxed integer. And so right now we're returning an unboxed integer, which is fine. So we need to do an I don't know. It's a pure function. They're all pure functions. I should actually decorate them as such. Okay, pure function, and we should say count leading zeros, machine bit vector return this, and now we might have to box it into a boxed integer. I'm not quite sure. I'm out of practice basically. Is there something to return? No, there's not. Okay. Return bit vector dot integer dot from int like this. There's lots of boxing and unboxing going on here, and if count leading zero becomes like a performance bottleneck, we have a bunch of things that we can do to fix it. So what's going on now? Print string takes exactly 2 arguments, 3 given. Apparently I have a print string that I'm not using correctly. Wow, that's impressive. And, oops, no. No, print string takes a single string. Why? Wait, what? I'm very confused. So apparently print string takes many strings on this level. I don't know why. I mean, dealing with all these weird internal functions is one of them, by far one of the most annoying parts of Sail. Print string. Oh wow, right. I don't have a print string at all. Def print. Okay, let's add a print string. That's easy enough. Def print string machine star args. And let's inspect things. Yeah, all these weird tuples, by the way, is a very strange OCaml property. So OCaml functions that take no arguments don't actually take no arguments. They take a unit. Did I not remove the make down? I didn't. They take a unit, and a unit is basically like a tuple of length 0, and I mapped this to a tuple of length 0 in RPython. Print string takes. I'm confused. Maybe there's a print string in the support code CHERIoT. Yeah, there is. Okay. Let's kill it. Cool. And while we are doing that, risk 5, support code risk. We can also kill it here. Okay, what's the args? So it is getting 2 strings. That means we're not printing them like this. We're printing them like, I suspect there's a space between them or something. Try again. Ooh, wow, it's doing something. Cool. It's happily chugging along and running Cherry instructions. I'm getting a tag violation though. That's probably not good, right? Yeah, it's an infinite loop. Yes. Yeah. So it's trying to do something, then it's getting a tag violation. I mean, this is an architecture that has sort of a lot more security features, and so basically when you try to access something that you're not allowed to access, you crash, and it's just crashing here, right? And it's, yeah, and then it's trapping from machine mode to machine mode, and then it's just doing the same thing again, so it's crashing again, and then we're in an infinite loop of trap handlers basically, right? Let's commit what we have though. Yes. No. Let's do the print string first. No. Yes. And now we can do the count leading zeros. Yes. Zeros. Okay, so what we need to do now is we need to find out why the weird capability exception is happening, because I mean it shouldn't somehow, yeah, I don't quite know what's going on there, and basically we need to stare at the logs a little bit. So if we run the tests, let's just put everything into an output file. Instructions CHERIoT.log. I suspect it's something silly. I suspect that we're setting up something in the wrong way just right after we start, right? Because this is the very first program we run, so it's very likely that we're getting something wrong very early. I mean, the other option is that we're getting a really, really weird, I don't know. We could have a bug in one of the weird bit vector operations, which leads us to conclude that the capability that we need isn't there. It's also a plausible source of the bug. But what we'll do now is we will compare the log that we get from Pydrofoil. We will compare it with the log that we get from the sail-based emulator, right? So we need to find out how to get it into the state where it's tracing output. Oops, cannot do that. Why not? Is it sensitive to ordering of arguments or something? Trace output. No. Ah, right, no. It's minus trace simply. Yeah. Okay. So let's put that. Oops. Pydrofoil CHERIoT. What did I call the file? Instructions CHERIoT season. Let's run that. Right, and it's done. And so now we can basically head instructions CHERIoT. Right. Right. So it is running a bunch of instructions successfully, and then it stops at some point. Right. Let's actually look at them next to each other, or we can also do I have a vimdiff or something? No, this might be a terrible idea. Yeah, the file's too large for this. Okay. Yay, it's large enough to crash my terminal. Annoying. Okay, I'll close this. Can I even just open them in? Yeah, it's huge. Yeah, but here we're trapped in this endless loop, right? Okay, let's tag violation. So the tag violation happens already early, and then we stay in the loop. So the error happens in let's see. The error happens in instruction 22, and we need to find out why that is. And so we can diff the log here, 22, and there's no tag violation in the Cherry code, in the sail-based emulator. There is only a single tag violation much further down after like 500,000 instructions. So there's something going wrong in instruction 22, basically. And now we can do this next to each other, maybe. Like this. Right. And it looks like we're already, like, even instruction 22 is already at a very different place. So something is very, very wrong. Okay. I will cut off both files at like instruction 50 maybe, because the problem happens before anyway. And then I can inspect the files a bit more carefully. And I can also remove the test stuff. To host located. elf entry, CSR. Yeah, it's doing something wrong, and I remember this, I think. So in let's think. In Pydrofoil, it's not running at the elf entry point at all. Instead, it's running somewhere in emulated ROM, and this is was always a controversial thing. The RISC-V emulator has some kind of weird emulated ROM that we're setting when we start, and it seems we should just not do that. Post. Yeah, it's here. This is the reset vector that is getting automatically filled when we start the machine, and it seems that the C-base emulator is not doing that at all. It's just directly starting at the 2-host code, I think. Yeah, the mstat is the same, but then it starts at the wrong PC. So let's see where that happens. Init_sale, we will just not do that, right? And let's also kill this. Yeah, it's doing the ROM thing, and I think in CHERIoT we simply shouldn't have a ROM. So where do we set the entry point? What do we do with it? We write it into the ROM, and then what? Right. And so I think what we should do, we should say we boot at the entry point. So instead of initting the reset vector, we will boot at the elf entry. Okay, and this is xxx unused. We can also just kill it. I think I will kill it because this is a weird RISC-V thing, and it might even be going away in RISC-V as well. So okay, let's try. Let's try. Here. We can run it again. It's doing things. Okay, but it's going into a tag violation again. Why is that? But later, right? Okay. Let's put that into a file. Does this work? Yes. And troops CHERIoT. What did I call the file? Instructions CHERIoT. Here. Right. Now we can see elf entry, blah. And now it's doing something better, maybe. So it's doing a LUI instruction in both of them. But no, X13 is right. But this looks different here. This is a capability, right? So why do we get different capability strings here? Right. Then we do an add I, and again, X13. I think X13 is the what is X13? I don't know. It's just a general purpose register. Right. So it does add I, that's fine. that sets the value here. Then it comes at IA10, at IA10, that writes this value, and then C special RV C4 blah 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 null, C null, and that's the capability A4 that writes X14 to this value, and here the value is different, right? So something is different in the capability bits somewhere, and that's obviously very concerning, right? Because I mean, I would have hoped that if we're missing something, we would just get errors, but now we're just getting wildly different capabilities, permissions, whatever this thing here is, and just that just looks very scary, right? And yeah, so this is the next thing that we'll have to fix. But yeah, I'm going to like call it quits now, because I've been going for like almost 2 hours, and this looks like a large complicated problem that I might not like find out immediately. We can see that it keeps going for a little bit, but then like the capabilities are always different, and at some point it tries to do something that it's not allowed to do, right here, and then it just gets stuck in the tag violation loop. Okay, I think that's it for me today. Thanks for everybody who joined in. I'm not really sure whether I can do this more regularly right now. I mean, I did most of the streaming 2 years ago in the or even 3 years ago in the pandemic, and I just have it's not clear to me that I can do more of it. But it was fun to like at least do a session again, and we can see whether I have more time or maybe a little bit more of a focused topic. Thanks everyone, and see you next time.